Okay, so let's talk about normal or Gaussian distribution functions. Normal distribution functions, this is the bell-shaped curve, and usually we're trying to find the probability, which is the area under the curve for a certain range of values x. And so the function for the Gaussian or normal distribution is this one. It's the e to the negative x minus the mean squared divided by 2 standard deviation squared. So you need the two parameters, the mean and the standard deviation, and that defines the whole function. But this is a complicated function to integrate, and it's not very friendly for just easy math. So some of the options for finding the area under the curve are using your calculator's numerical integration function. It may actually have a normal distribution function built in if you read the help. In MATLAB or Octave, the MATLAB clone, there's a function called norm CDF where you give it the value x, the mean, and the standard deviation, and it will find area under the curve. With either of these, it's pretty easy to find the area under the curve. Say, here's the mean at 2, and if we wanted to find the area between 1 and 3, we could do that with any of these functions. But what's difficult is if you know the area you want and you're trying to find the value of x, the limits of integration here, either a or b or both, are difficult to solve for using these numerical techniques. Because of that, we have this table in the book. So we're going to start into a lot of tables in this class. So table 6.3 is a table of the areas under the Gaussian distribution. And to make the table that works for any value of the mean and the standard deviation, we make this non-dimensional parameter z that's defined as x minus the mean divided by the standard deviation. So you take x and you can find z, and then you can find the area that goes along with that x from the table. So just looking at this equation, we can see that when z equals 0, that's when x equals the mean. So when we have z on the x-axis, the peak is always at z equals 0. Z equals 1 when x is 1 standard deviation above the mean. Z is negative on the left side of the mean and positive on the right side of the mean. And this table we'll look at next. So we'll get to the numbers on the next slide, but a really important thing is to notice the area that's given in this table is the area shaded in this picture. So between the mean and z, which you get from x, and the mean and the standard deviation, we get this area. So sometimes we need to include this other half. Of course, half of the distribution has an area of 0.5 because the whole area is 1 and it's symmetric. So we're usually doing some combination of the area from the table and the other parts of this shape. And the other thing to notice is that the area table doesn't have any negative values of z's, because by the symmetry here, the area of negative z is the same as the area of positive z, so just flip the sign and go into the table for that case. There's one more confusing thing about this table 6.3, and it's just to make it very compact. So what we have is the value of z, and we just have the area as a function of z. So it's really just two columns, but to make them fit into this table, they run across the rows. So the z column here is the tenths, and then up here is to the hundredths. So if you want the area for a z of 0.32, here's the 0.3 row. This is 0.30, 0.31, 0.32. So the area of z of 0.32 has an area of 0.1255. And that's this area between 0 and 0.32. So that's how we use this to find the area under the curve. So what's really important is when you're doing any of these Gaussian problems, sketch this curve, shade the area you're interested in from the problem, and then go into the table. It's really, this table is confusing, it's all very compact, but you want to have a good picture of what you're headed for and it really helps with the partial credit on tests too. Okay, so here are some examples. So in this case, we have the mean of 3, standard deviation of 4, and we want to know what is the probability of a measurement being between -5 and 11. So we're going to assume a normal distribution. Usually when you see these two parameters, you're going to assume a normal distribution or Gaussian distribution. And we're going to sketch the curve, but just writing out the probability using the definition of probability distributions, it's from -5 to 11 of the Gaussian or normal distribution function with a mean of 3 and a standard deviation of 4. So you could plug that into your calculator and get the answer. Okay, so let me try sketching this out. I'm going to draw the curve. There's our Gaussian distribution. The mean, where the peak is, that's at 3. And I want to know what the area is between -5 and 11. So this is a sketch of the area that we're looking for this problem. We've got x on this axis, and the Gaussian distribution is the y-axis. Okay, so now we want to use this table to find this area under the curve. So the first thing is to convert the x values to z values using that equation. So if we have x equals -5, that gives us z is -5x minus the mean, 3 divided by 4, so that's -2. And for x equal to 11, we have the z is 11 minus 3 divided by 4, and that is +2. So we've got some symmetry here. So if we sketch this again, we should see something like this. Now we've got z here, and 0 is the mean on the z-axis, and we've got +2 and -2. And again, this is the area we need to find. So now we can go to the table and try to find the areas for these values of z. So for a z of 2, we go right in here, and we've got the area of 0.4772. So this area, 0.4772, big old decimal point. That's just this half. Then for z of -2, we don't have negative numbers in our table, so we use the symmetry, so it's the same as the +2 in this case, so it's also 0.4772. So the total area under the curve from -2 to 2 is twice this, so it's 0.9544. So 95.44% could be our answer. Okay, so now let's look at the same parameters with the mean of 3 and the standard deviation of 4, and now we're looking at the probability of a measurement being greater than 6. So again, we always want to sketch the curve. So draw a sketch. The mean is going to be here. I'm going to do this in z, but this would be at x of 3, but in z it's always 0. And then for a measurement greater than 6, that's bigger than the mean, so it's going to be on this side. And that's going to be a z of 6 is our x, minus 3 is the mean, divided by 4, so 3/4, so z of 0.75. That's our x of 6 value. And then for the greater than 6, it's the area between 6 and infinity. So the probability of a value being over here between 6 and infinity, that's the area that we need. Okay, so now we can go to the table and try to find this area. So remember, the table gives us the area on the left of the z value from 0 to z. So for a z of 0.75, here's the 0.7 row, 70, 71, 72, 73, 74, 75, right here, 0.2734. So that's the area on this side. And we want to find the area on this side. So our area is going to be 0.5, which is the whole area here, minus 0.2734. So that is 0.2266. .66%. You can read that. So that's how we use this table in order to find the areas under the curve and try to find probabilities. Okay, for the last example, we're going to look at this lighting department maintenance problem where we have the lighting department of a city installed 2,000 electric lamps, an average life of 1,000 hours, standard deviation of 200 hours. So whenever you see the mean and standard deviation, think Gaussian problem. How many lamps are expected to fail between 900 and 1,300 hours? First problem. So first let's sketch that in and try to find the probability of failure between 900 and 13. So we always start by drawing the shape. So here's our mean is 1,000, and we want to go up to 1,300 and down to 900, and it's this area that we're looking at for part A. Okay, so the next step is to convert the x's to z's and find the areas. So for an x equal to 900, we have z is 900 minus 1,000 divided by 200, which is negative 0.5. And for x equal to 1,300, we get a z 1,300 minus 1,000 divided by 200, and that is 1.5. Okay, so now we can go to the table and we can find the area. So with the z of 0.5, we've got the area right here. A is 0.1915. And for this one, the area of 1.5, 0.4332. So if we add those together, we get a probability of 0.6247. So that's our answer to part A, 62.47%. So 62.47% are failing, but this is not asking the percentage, the probability of failure, it's how many, and we have 2,000 lamps. So 62.6247 times the 2,000 lamps that we have gives us our final answer, which is 1,249. Lamps. There we go. So that's our final answer, 1,249 lamps, which is 62% of our 2,000. Okay, so now for the next part, part B, we're trying to find how many hours, at what hours would we expect 10% of the lamps to fail. And so this is again where you really want to start off with a sketch of the Gaussian distribution. So think about 50% failure we would expect at the mean, right? 50% would be failed here, the average lifespan. And 100% would be, up in infinity, and more than 50% would be higher than the mean, less than 50% would be lower than the mean. So we're going to be down here somewhere where the area, this area, is 10%, 0.1. So that's what we know, the 10% failure right here. And so we want to find this z by going backwards in the table. So this is harder to do with direct integration. Okay, so the area is 0.1, but the table doesn't have the tail areas. It has this area, actually the area on this side of z. So we want to find this area, which is going to be 0.4. So this area, if this area is 0.1, then this other area would be 0.4. So we look in the table for 0.4, and it happens to be off the scale here. It's off to the side there. But you can trust me that the area of 1.28 equals 0.4. So that's our z value. There's a couple of tricks here. We had to do this trick to get the 0.4, but this is actually 1.28 over here. And so our actual z is negative 1.28 because it's on this side, not this side, using the symmetry. And so using a z of negative 1.28, we can find that x is z times sigma plus the mean, and that is negative 1.28 times the sigma plus the mean, and we get a value of 744 hours. All right, so that's the answer for part B. 10% of the lamps fail, and it's a good check. So at 1,000 hours, we would expect half of them, so we're below that. That's a good check. If you forgot to flip the sign here, you would have said something above 1,000 hours, and that's a good thing to pick up on. So start with a shading, really think about where your areas are coming from, then go into the table and try to get to your solution. Okay, so that's enough with that stupid pen. So this is just a summary now of the basic shapes when we're doing probabilities using Gaussian distributions and where you find them in the table. So this is a little bit sketchy looking there from my notes, my lecture notes, but I think you'll be okay reading them. So basically the probability that x is between x1 and x2, that's just the area under the curve. But using the table, it depends on whether x1 and x2 are above or below the mean. So if x2 is greater than the mean and x1 is less than the mean, then we have this shape. And we can go into the table and find this area is the area of z2, converting x to z, and this area is converting to x to negative z, because this will be a negative z. So we flip the sign in there and find that area in the table. So we'll have two positive table areas. So if you can see here, this is one possibility. The other possibility is that both x1 and x2 are less than the mean. So it's this area from x1 to x2. So then it's the area in the table of negative z1 minus the area in the table from negative z2. Similarly, if they're both above the mean, it's the area of z2 minus the area, this little sliver would be the area of z1. So we're just adding and subtracting the shapes to make these work. So any probability is going to fall into one of these categories. Okay, so for the probability of something being between a value and infinity, we have the greater than and the less than cases. So these are the possibilities. If we want to know the probability of x being greater than x1, if x1 is greater than the mean, then it's this area. Greater than x1 would be all of these areas here. So to find this shaded area, we take the whole area, which is 1, and we have to subtract off the white spaces, so we subtract off the 0.5, and we subtract off this area that we would get from the table. And that will give us the probability here. If x1 is less than the mean, then we just add up the shaded areas. So this side is 0.5, and this side is what we would get if we use negative z, because z is going to be a negative number. We want a positive number here. So finding the area from the table of this one, add them together. Probability of being less than an x1. If x1 is less than the mean, then it's this little shaded tail here. It's very similar to above, where we've got the whole area is 1 minus this white area is 0.5 minus this area that's from the table, and that gives us the shaded area. Same thing here, if x1 is greater than the mean, then we're just adding shaded areas together, 0.5 plus the area from the table. Okay, so that should give you some practice with using the table for Gaussian areas for normal distributions. That's how we're going to use it in this class. I saw the calculator ways, and you can use MATLAB, but for this class we're going to focus on using the table as our solution technique. So print out table 6.3 and make a couple of copies so that you can mark it up when you're solving problems. It's really helpful to be able to underline with your pencil what row you're on and everything. So print out a couple of copies to keep on hand. And I'll see you in the next video.